So taking these issues into account, I'm going to briefly survey related work in virtual networks. So virtual private networks are not new. They have existed for several years. There are enterprise VPNs connecting you to your university or your business. There are open source VPNs like OpenVPN, consumer grade gaming type VPNs for connecting resources across small businesses or across residences. Hamachi is one example. And these technologies are all VPN technologies, virtual networking technologies, but they're not easily applicable in the context of intercloud virtual networking. Some of these are proprietary code, and even the open source code like OpenVPN is very difficult to configure and manage, and you have to set up gateways and you have to set up the configuration of these systems in a non-trivial manner. It's difficult to scale. The more sites you try to put together, scale in terms of configuration and performance. So some related work in the context of grid and cloud computing have emerged in the last 10 years or so to address some of these issues, and again address the fact that virtual machines require virtual networking, and in many cases put much stress in the need for virtual networking because you have to create more entities that are connected to networks. Violin is a project by Dongliang Xu and collaborators at Purdue University, one of the first published overlay virtual networks targeting connectivity among wide area virtual machines. So the key ideas that were put forth in Violin included a fully software-defined virtual execution environment. So the network had virtual switches and virtual routers that were programmable, and the end hosts were virtual machines. So that creates this idea that you can have a fully decoupled independent address space, virtual machines connected across multiple domains. It did not address issues of nets and firewalls, which can become a problem in practice. Vinet from Northwestern University and Peter Dinde and collaborators over there was also among the first works published in this topic. A key idea here was a layer 2 virtual network, which allowed a user to extend a LAN to remotely hosted VMs, much like Amazon VPC, but at layer 2. Vinet is still an active project, and in recent work it has been moving to go within a virtual machine monitor for fast, high-performance packet processing, including gigabit and 10 gigabit per second Ethernet virtual networks that can deal with that level of throughput. Vine is a project also at the University of Florida by Mauricio Tsugawa, Joseph Fortes, and collaborators. And the key idea here was a managed layer 3 virtual network architecture, allowing virtual networks to be deployed across multiple administrative domains and also dealing with the connectivity constraints of nets and firewalls. Vine is organized much like the internet with routers, and the routers can be used by nodes in local area networks as gateways to the overlay. And these routers are programmed through Vine APIs and Vine interfaces that allow routing tables and the creation of address spaces and the like. For net traversal, firewall traversal, Vine relies on routers on the public network that can buffer and forward messages in the overlay for devices that are constrained by rules in the nets and firewalls that prevent incoming packets, for example. Vin is a project at Vrije Universiteit in Amsterdam, Thilo Kilman and Kees van Reeuwijk. And the key ideas here is that this is part of the Contrail project in Europe, and as part of this effort, the key idea was that they wanted to have a virtual network that does not rely on user-level routers that are not part of standard distributions of operating systems. For example, the systems that I described earlier, as well as IPOP, are user-level virtual routers that can introduce overhead, can introduce potentially new failure modes, and the approach with Vin was to be able to, when possible, when it's possible to connect directly resources. For example, if they're not constrained by nets, that you create an overlay using kernel level primitives for tunneling. It's also a layer 3 virtual network, also based on a management structure where you have agents running on the endpoints and a central VIN controller. So the agents are responsible for interacting with the kernel to set up, create, and tear down tunnels. And the controller is responsible for communicating with the agents and orchestrating them to set up and manage virtual networks. And invent tunnels can be secured using IPsec technology, which is also, again, available in operating system kernels. And finally, IPOP from the University of Florida. I'm involved in it myself and Oscar Boykin, formerly at UF, and our collaborators. The key ideas here were that, compared to previous work, we wanted to support routing tables that are self-organizing rather than managed. And they use a structured P2P topology for fault tolerance, self-configuration, and scalability. Another key aspect was net traversal in a decentralized fashion, not requiring centralized servers to negotiate the traversal of nets. So in the next few units, I'm going to delve into the details of IPOP and how these features are supported, and that's going to be also the virtual network we're going to use in hands-on activities.